Hello, everybody. Thank you for joining this webinar about how to ensure e-motor efficiency and cooling performance while maintaining MVH target. So, we will introduce to the efficiency multiphysics simulation using three product. So, this webinar is present by Hexagon and PowerSys company. So the agenda of this webinar is divided into four parts. So the first part, I will try to present the loss and force calculation into JMAG. So this part will be presented by myself. So I am Didier Zefrak from JMAG support team at PowerSys company. The second part will be presented by Maxime Beaumet from Hexagon. So it is a scFLOW CFD engineer. So he will present the cooling performance and design modification in scFLOW. So and the third part will be presented by Roman Bosson, also from Hexagon. So it is Actran engineer. So he will show you how to analyze the noise vibration using Actran. And before ending this section, we will try to answer any question that you will ask. So please feel free to type into the chat box from the GoToWebinar panel any question that you will have. So regarding my part, so about JMAG, so note that JMAG it is finite element tool that allow you to design and simulate any type of electrical machine. So this tool was developed since '83 by Diesel Corporation, which is a Japan company based in Tokyo. So with JMAG, we can design, develop any type of electrical vehicle and also a transformer. So regarding the internal analysis that we can do with JMAG, we have 5 types of analysis. But today, during this webinar, we will focus on the magnetic field and iron loss calculation. So regarding JMAG, so note that it is a finite element software developed by Diesel company since '83. So it is a Japan company based on Tokyo. So with this tool, we can develop electrical motor and also transformer. So for the analysis that we can do with JMAG, so we have 5 analysis. So, but today we will focus only on magnetic field and iron loss calculation into this part. But know that into JMAG, you can also make a coupling analysis using this internal analysis. So if we apply this analysis into motor test bench, we can see that we can obtain different physical quantity. So in general, note that with JMAG we can simulate any type of machine that is usually used into different industrial sector. Regarding the advantage of JMAG, so one advantage is that if you look the different step to design the motor, at each step the JMAG provides you a specific tool. So for example, for the starting point of the design, you can use JMAG Express for rotation motors. So with this tool, you will get in 1 second the basic geometry and the basic characteristic of your motors. And then you can switch on JMAG Designer for detailed simulation. Into JMAG Designer, you will be able to make some fine mesh to add some specific condition in order to get the good result. And then for the testing and validation, you can use JMAG RT to convert the 2D or 3D finite element into 1D component that you can import into your software or test bench. And you can automatize all this process by using JMAG VTB. You can also able to couple JMAG with some external tool. That is the topic of today. So I will not detail the internal feature of JMAG, but I just want to mention that JMAG provides you also some tool that allow you to communicate with external software. So regarding the loss calculation, it is very important to understand where the losses is generated inside the motor and to see how this loss is translated into the temperature in the part. So JMAG will allow you to calculate the losses generated by the variation of the magnetic field, so the iron losses, and also the loss generated by the current which flowing inside the conductor, like the coil or the tank of the motors. So regarding the particular calculation of the iron loss, so note that into JMAG you have a lot of method to get the losses, but the iron losses is calculated into the post-processing based on the harmonic distribution of the magnetic flux, the electric cycle, and also based on the iron loss density data, so the iron loss property of the material. So into JMAG you have two types of loss properties. So you have the iron loss density, and you also have the hysteresis losses that you can also use to obtain the iron loss with high accuracy. So regarding the force calculation, it is also important to understand the deformation and the noise produced inside the motor. So this noise generated is produced is due to the electromagnetic force generated inside the motor. So for that, we know that we have different sources of vibration, but today we want to show you the vibration due to the electromagnetic forces when the motor is powered by the current. So regarding the method to calculate the forces into JMAG, we have different method. So we have the nodal force method. This is to calculate the forces of torque into the magnetic material. This calculation will use the Maxwell tensor. So we also have the second method, so the Lorentz force calculation. This is for the non-magnetic material such as the coil or the other conductor that you have into the motors. So, and the last one, it is the surface forces. So this is to calculate the pressure or the surface force on the contact phase between two magnetic parts. So then I will start with the demonstration. So I will start JMAG Designer. Okay, so I will open the demo model. So here, this is the JMAG interface. So here you have the preview of the project. So you will have all the model and all the study that you have done. So here into your right, you have the toolbox. So in the toolbox, you have the material database. So here you have different type of material. So you have ferromagnetic material. So here I can show you the properties. So you have the magnetic property, so the BH curve, and also the other property. And here you have the loss property. So this is the loss density property. But you can also implement or use the hysteresis loss. So here you have the symmetry loop of the complete hysteresis property. So this property can help you to get the iron loss with higher accuracy. So from the toolbar, you also have here some condition. So but here, this is my full model. This is the reference model. Here you have different part of the motor. So based on the symmetry of this motor, so I create the quarter model here. So the quarter model here. I also create this reference study. So to check the different analysis that we can apply to this model. So here you have the list of the analysis that we can apply to this 3D model. Here you also have the efficiency map that we can use to generate the map of the efficiency. Okay, so here this is my reference today. This is all the material that I apply to each part here. This is also the condition. So here you can see the different condition that I apply. So here this one is to define the periodic boundary because I model the quarter part of the machine. So this is this FM coil condition is to define the configuration. So this I have done it manually, but you can also use the winding editor tool to do it automatically. So this winding tool is very important when you have a large slot inside the starter side. Okay, so here I can also show you the circuit. So this is the circuit. Here I will power the motor by using some sinusoidal three-phase sinusoidal current. Here I can show you the winding connection. So here you have the three-phase winding. If I duplicate here, you can see the characteristic of each coil. Okay, so I can also show you the mesh. So this is the mesh that I generate here. So to calculate the forces, I need to go to the condition box. Then I will apply here. I will take the force condition, apply to the stator. Here I will define the name, example. Okay, so this condition will allow me to calculate the forces inside the stator. I can also apply the iron loss condition for to get the losses from the rotor and the stator. So here I can define the name. Yeah. So here you have a different method to calculate the iron losses. So you have preset 1. So this is the standard method, and you also have preset 2. So preset 1 will use the apply loop. So it will calculate the corresponding, so the surface of the loop at each amplitude of the magnetic field to get the hysteresis losses. And you also have the FFT, the FFT method for the Joule loss calculation. So in this method, so JMAG will apply the FFT on the magnetic field and at each harmonic of the magnetic field, and based on the material data, so it will calculate the Joule losses. So for the advanced method, this allows you to use the hysteresis property, so the hysteresis model, to calculate with higher accuracy the hysteresis losses. Also, you can use the edge current in circuit method to get with high accuracy the edge current losses inside the steel sheet. So here you can also specify the property of the steel sheet, like the thickness. So I will keep the standard calculation. So here you need to define the number of pole of the motor. Here the speed, I think, is 2000, or you can directly define the frequency. Yeah. So when you have done this, so now you are able to run the calculation and get the result. So I will not run the calculation. I will directly show you the result that I got. So here I can show you the third curve and also the iron losses. So I can also show you the distribution of the magnetic field. Yeah. So I can display for the full model, so for the complete model. So I can also show you the iron losses inside the rotor and the stator core. I can show you the joule losses distribution inside the copper. And to finish, I can show you the forces, yeah, which act on the stator core, on the two of the stator. So now when you are finished to calculate, to run the simulation and get the result, so now you can use the multipurpose file export tool to export the JMAG result into a specific format that you can use into your external tool. So for the thermal analysis using scFLOW, you can use MSA Nastan 5 format or CSV 5 format. So for example, if I use Nastan 5 format, here I need to specify where I want to save my output file. So here I will save it here. Save process. So the extension, I will say PDF file. So here you can see you have different extension. So, but with scFLOW, with the communication of with scFLOW, we generally use .bdf file. See, here you can also select which the type of analysis that we want to do into the external thermal software. But here I will keep a static simulation. Here you need to define which physical constraint you need to extract. So here you can say this file, this is the geometric result file that I got here. So I will edit it, and here you can see that here you have different parameters. So the first thing to do is to select the path where you want to export, for example, the losses. So here I want to export firstly the losses from the copper and also the magnet. Yeah. Then here I will select the joule losses here, and because I am using the partial model, so the quarter model, I need to convert the result to get the distribution on the complete motors. So here you have the method, the mapping method with the meshing of the external software. So here you can use the direct mapping when the mesh from the external tool is very coarse, and we using distribute force density mapping when the mesh from the external tool is very fine, and when we want to extract the distribution of the physical quantity. So here I will select force density, and here you can also modify the coordinate in order to match the coordinate system of JMAG and the external software. Then click on OK. So here I need to select the support, so the support for the exportation. So the support is the mesh data. So here I will tell that I want to use the mesh coming from the JMAG result. So here this result file contains only the joule loss from any conductor. So here we also have into the calculation folder of JMAG, you need to select the loss file. So this is design loss file. This is the result file of the iron loss. Okay. Then here I need to select the stator core and the rotor part. Then here I will select iron loss density. So I do the same. I use the same parameter to convert to get the distribution on all the complete rotor and stator card. Here I will select force density. Then okay, so when you have finished this, now you can click on export. Yeah. then it will export this all the losses into this file. That is finished. So here I will also do the same for the forces. So for the forces, I will show you how to export into a CSS file. So here I will modify. So here I will say forces. Here save. And here I will remove the loss, the iron loss result. Here I will edit. So I will delete all the parameter. So here the forces, I will only select the stator. And for the quantity that I want to export, I will select forces, without forces. Here I keep the same configuration here. Okay. Then I will say export. Maybe I can show you. Then now I can show you the content of this file. So here, for example, you have, I will show you for the losses. So for the losses here, you have all the information about the analysis that we have done into JMAG. Here, you have the information about the number of elements into the meshing. And then now here you have the data. So here you have the ID number of the element. Here you have the coordinate of the element. And here you have the node. So the loss density of each element. Then for the forces, here I can show you the forces. So here for the forces, here you have the number of node. This is the ID of node. This is the position coordinate of the node, and this is the component of the nodal force at each node. Yeah. Okay. So, okay, so here I show you my path to get the losses and the FEA method. So this is the step that I follow before. Then now my colleague Maxime will show you how to import this data into scFLOW. Yeah. So Maxime, I will make you presentator for the next.
Thanks.
Now you can start your presentation.
Perfect. Thank you, Didier. Please tell me when you can see my screen.
Yes, now we can see your screen.
Okay. Thank you, Didier. So as Didier said, I'm a pre-sales engineer for the CFD Cradle tools, so the CFD solution at Hexagon. I would say as a pre-sales engineer, I'm very lazy. So that's why I always start with wondering why I should do something. So in this case, we are designing an e-motor. But the question is, why should we care about thermal behavior? Because, you know, if you don't have to put your finger on, maybe it's not a big deal. But as I am also a simple guy, I always defer to experts when it deals with specific applications. So in this case, I took some quotes from smart guys that know what they're talking about here. And it seems that for motors, the heat behavior will strongly affect the performance of it. So it can act on the efficiency, on the life cycle, and so on. So it can be very important. And the very interesting point is that when you are at the design stage, maybe for no potential additional cost, you can increase the efficiency of your motor. So it begins to be interesting here. Another point is that it looks to be very complex to solve a temperature, a behavior, a thermal behavior of an electric motor. So that's why maybe we should consider something maybe stronger than a wet finger to estimate the thermal behavior of a motor. So still basing myself on their quotes, I was wondering what can we play on to improve the motor efficiency, the motor heat cooling. So it appears to have three main solutions. The first one is about material properties. If you increase the material properties, you will increase the heat dissipation. That's the first point. The second one is about passive thermal design. It means that you will design the motor in a way that natural convection can help to cool it down. And the last solution, when natural cooling is not enough, you can increase it by adding specific cooling channel. So what we call here active convective cooling. So based on these three different solutions, I think that CFD could help here, because in CFD we will input the thermal properties of the different materials. We will also calculate airflow or liquid flow, whether if it's natural cooling or forced cooling into channels. So I definitely think that CFD could bring something. So now we know that we need CFD. So why to do it with scFLOW? You know, I'm the pre-sale engineer of scFLOW. So of course, I will tell you that this is the best tool of the world. Actually, it is. But anyone could tell you my stuff is the best one for you. So instead of telling you just that assessment, that claim, I will just show you why this tool is the best for you. To be honest, I'm working in a CFD company, but fluid dynamics, it was a nightmare for me when I was at school. And to be honest, I don't really understand people that are keen on this kind of equation. It's very complex, but that's a good point for them. But personally, I'm not. The good point about scFLOW is that this complexity is becoming so easy to solve, because maybe this is because this software is designed in Japan. Because my Japanese colleagues, I really love them, they have this idea of pragmatism based on this very simple statement. You don't need a PhD to have CFD problems. So you should not need a PhD to be able to use a CFD solution. That's the way they design our tool here, scFLOW. They design it in a pragmatic way. You have problems, we have a tool to give you solution in the shortest amount of time. We don't expect you to spend hours on CAD data cleaning, on putting some turbulence model and so on that you have to design on your own and so on. It's very pragmatic, ease of use. But as I said, I'm just a pre-sale engineer. I'm French, I'm working for Cradle, so you have no reason to trust me. So let me show you this software, and after that, you can make your own judgment, okay? So I will switch to the software itself. So here, basically, since this presentation is a little bit short, so I have started already. So basically, I have imported the geometry. So the same model than Didier showed you previously. I have imported the geometry. I have just created here a plenum around it, because that's always the same story. In the CAD software, you will get the solid parts, but for CFD, we are not only interested about the solid parts. Of course, it will be important for the heat transfer. But of course, since we are dealing with convection, the air or the fluid, it means that you also have to create this volume. So in this case, I just create a plenum around my system. Based on that, here, so in the interface, so it's very easy. You go from the top to the bottom to the resolution of the simulation. Here, we will set up the material properties of each solid. So in this case, for example, this volume that I created, actually I created another one here for the moving area. I will just pick them and tell the software that it's fluid. What kind of fluid? Is it a gas? Is it a liquid? Is it compressible, incompressible? So we have existing libraries with fluids and so on. Of course, you can create your own one, if not fulfilled enough here. So the same here for the different parts. So for example, the housing, the support, Let's make it simple here, for example. Okay, the rotor as well. Okay, now this time for this solid, it will be based on the solid library. Maybe it will be made of, I don't know, PVC as an example, okay? For the coils, of course, no plastic anymore. We'll switch to the thermal metal properties, so copper in this case. And for the magnets, I will just pick iron properties. Let's make it simple. Here, we are only dealing with thermal properties. Okay, so that's for the properties. Now we can register a region. So a region is one or a group of surface that we want to clearly identify. It can be for several purposes. It can be, for example, to assign boundary condition. So in this case, I will just identify the external of my box here. I will just create bottom and top side. Other purpose possible to create region, it could be for meshing perspective. If you know that you will have to refine locally the mesh, you can also create a region so that you can say in that region, I want to refine the mesh. And the last reason for why you could be creating a region, it can be also for post-treatment. If you need specific result in a specific region, create this region, and after that, you will be able to ask the software to automatically output results there. So that's for the region. Now we will set up the simulation itself. So here we have a wizard with different panels to fulfill to tell the software what we want to solve. So don't worry, I won't explain each one of them. It would be fastidious and painful. I will just focus on what really matters in this case. So here, first one, analysis type. This is where you can add physics to be solved or not during calculation. For example, if you are also interested by particle tracking, for a reason, maybe you want to monitor, for example, dust in your system. So you just have to add a physics, and then you will get an additional panel where you will have to give your inputs in this specific perspective. So here we are dealing with a flow calculation. Of course, you can also go in deep about the way you will solve the flow. For example, if you are using runs, if you are using LES, if you are using density-based solver, pressure-based solver. And by the way, if you don't understand what I'm talking about, don't worry, because we provide the solution, but we also provide the methodology to use it based on your application. As I said, we don't expect you to have a PhD in fluid dynamics to be able to use it. We are also here to support you, I would say, on the daily purpose. So that's for the physics. Regarding here basic settings, as Didier said, we can solve steady state simulation. So we are just looking for an equilibrium. But we can also be interested about transient results. After how much time do we something? As soon as you have time in your expectation, you should switch to transient. In this case, I will just remain on static, even if I know that the rotor is moving, but we can consider rotation even in steady simulation. Regarding the boundary condition, that's why it's important to identify regions, because here I can say, for example, on the bottom side, I know that I will have a pressure reference, maybe the atmospheric pressure, okay? Let's remain on 0 Pascal, sorry. On the top side, maybe I can just say, okay, it's open to the air. That's it. We can also say, for example, that the side here of my plenum, there are virtual walls, so I don't want any pressure loss to be calculated along them. So I will just specify, okay, just virtual walls. And since we check here the heat solution as well, we also have thermal boundaries in which we could say, for example, that on the side, we'll be dealing with, for example, ambient temperature at 20 degrees, it's open to the air, and so on. So this kind of information, so we'll just give the context of the motor, what is around. It's ambient temperature at 20 degrees, okay. For the motion of the rotor, as I said, even if we are solving a static simulation, we can consider that this rotor will be in motion. And as you may know, this rotation speed will be quite high. So of course, it will influence as well the airflow inside the system. So here we can say, okay, I have a group. So by the way, here you can see that in the tree, I have just sorted my part between the static one and the moving ones. So here you can see that the rotor and the magnets are considered as moving parts. So all these moving parts, I can just describe their motion. In this case, it will be simple rotation. It can be more complex if you have, for example, translation, rotation. We can also deal with 6 degrees of freedom. In this case, it just means that the flow is driving the motion of a specific body. So in this case, it's just rotation. We can specify the rotation per minute or whatever unit that you could be interested in. And then it will automatically suggest us a rotation axis for our part. In this case, it's a revolutionary part. it will suggest the right direction, but of course you can change it if you will. And you have also the direction of the rotation. Very convenient sometimes. So that's for the moving. But remember and keep in mind that we are looking for thermal behavior. So in this case, I have not specified anything about the heat source of this motor. If you remember what Didier showed us, it was calculated by JMAG. He has created a PDF file that will contain this heat source. So that's why I will just move here on source condition. I will select all the solid parts of my model, and I will tell the software, I don't know the amount of heat that will be set on these volumes, but someone knows. So I will just map results from outside. So in this case, Didier gave me this file, okay? So it's in the same folder than my CLT project. I will just move here to this panel, okay? And I will say the field for the mapping condition, that's that one. And that's it. So far, I have set up my simulation. The only left for me to do here is to deal about meshing. So for the mesh, we can do it in 2 steps. The first one, we set up the local mesh density, and then we ask for the mesh itself. So setting up this mesh density, we do what we call an octree. So an octree is nothing more than a preview of the mesh. So for example, here I can say, okay, I will ask 4 centimeters cell size on the surface of the different volumes, and I can allow it to go up to 16 centimeters. If I do it, in few seconds, I will get an estimation of the number of elements, and I will get as well a preview. So here you can see very low number of cells. Here, it's quite coarse, I would say, but for the plenum itself, it's okay. What about the motor itself? So for example, if I zoom a little bit around the housing, you can imagine that if I use this cell size for the housing, of course, I will miss a little bit of accuracy. So that's why we can also, so in addition to the global settings that I have already put here, convenient for the plenum, I can also rely on regions and the different volumes. So for example, here, I can just pick the different volumes of the motor, or just pick all of them in one operation here. Solid parts, I will ask for 1 millimeter cells, and I can also spread this modification to the next neighbors. And from that, of course, I will have more elements. Here we were talking about 4,000 parts. Here we are talking about more than 800,000. Of course, we'll have more cells, but in this case, if I still look at the housing itself, you can see that this time it should be fine enough to catch the geometry itself, because don't forget that the mesh is the way that the solver will understand your geometry. So this is why it should be fine enough to describe, I would say, your original CAD. And once you have set up here the cell size, you can ask for the mesh itself. So once again, very pragmatic. You have preset configuration, whether you prefer stable element, good quality, if you prefer, for example, to deviate a little bit from the original CAD, but on the opposite, if you want to remain straight on the original CAD, you can ask a model shape oriented meshing options. But if you're interested as well, you can also deep dive into the different settings, because for the mesh itself, you can master any aspect of the meshing process. So you can go into detail and ask the mesher to do what you want to do. Okay, so instead of launching the mesh here, I will just show you here directly what I have already done on this model. So here for meshing, we use polyhedral mesh. So here, if I show you, so here we have polyhedral elements, I would say in the fluid itself, also in the solids, and near from the walls, so where the fluid will have high gradient velocity, where we want to catch accurately what's going on, we have also some prism layers here. It's well known in the CFD world. You have this kind of flattened elements to be able to catch high gradients near from the walls. Okay, so that's the mesh that I get for this specific application. So if I just focus here, for example, on the motor, you can see that here I even refine a little bit more here on these openings. So that's for the setup. So far, I'm ready to launch calculation. So if I review results here in the post-treatment, of course, we'll be able to check, for example, the thermal distribution on the system. So here, for example, I can pick value of temperature. Okay, what is this temperature? Okay, so I would say that's the minimum. I can also check, for example, in cutting plane. I can move them as well. So, for example, what's going on inside the system itself. So here you can see that this plane can be cutting, can be not cutting, but whatever, you can do whatever you want. To be honest, if you show me a CFD result, I'm not able to tell you if it's coming out of our system or not, because you can customize whatever you want. For example, if you just want to compare this result to a thermal camera, you can also switch the way you see thermal on a thermal perspective, so you will have the color corresponding to thermal camera. So here I have the temperature. This is a status. I gave inputs, I get outputs. But so far, I don't get really the insight about why I have this temperature in my system. So that's why during the solving, we also have another result file here. We call it the it-as-view. It helps us to quickly understand what's going on in the system. For example, here in this case, my problem was that maybe the rotor was too high in temperature. Let's focus on the rotor itself. Here, I have the contribution about the heat released by the rotor and the heat received by the rotor. So here, of course, we have high temperature, so we'll focus on where this heat comes from. And you can see that here, nearly 70% of the heat is coming from the air. So maybe we have hot air around the rotor that contributes to this rise in temperature. So if we want to improve this temperature level, we need to improve as well the air circulation around this rotor. Based on that, we can go back to the CAD. So let's imagine that I'm smart enough to make some CAD modification and so on. So here we started with this housing, magic trick. I have made all my operation, and now I've created some openings. So I'm not telling you this is a smart solution. As I said, I'm not a smart guy. I'm a simple guy. But that's the point. Here I have an ID. I have a tool to check if it's a good idea or not. Maybe you have other reason to think that maybe it's silly, this kind of modification. But that's a solution I have in mind. So based on that, I can just export this housing. I will come back here in my setup. And in the CAD itself, I will just remove the original housing. So here, this housing, okay, remove it. I will just import the new one, so I don't need to import the wall model. I will just take the housing that I made. Okay, new housing. All I've done previously has been kept, including part material settings and so on. I just need to remesh, of course, because this is not the same geometry. And then you can rerun the calculation. And this time, you will be able to compare directly your two solutions. Okay? So here, for example, we started from this original configuration with something like 70 degrees here on the rotor. By adding these openings, I lowered it. So if we want to check, I would say the amount of benefit here. So 55 degrees. Originally, it was 70 degrees. So that's not a bad move. Maybe you can do something better, because maybe for dust consideration and so on, it's maybe not the best solution, but you can act. So if I summarize, you import your first design, then you run a first calculation. The software tells you a status about the temperature distribution. Then you can also get an insight to know why you have this statement in temperature distribution. So in this case, as you can see, we add some hot air trapped inside the motor. By creating these openings, we can see that now we have some fresh air coming inside the motor and going out. So it's logical, but it's always difficult to quantify. So that's why I think you need CFD, and that's why I also think that scFLOW is a convenient tool for you. So that's all for me. So I hope I was not too long. So Romain, I think Didier will give you the lead now.
Thank you, Maxime.
So yes, so now I will make Romain presentator. Let me know if it's okay from your side.
Let me know if you can see my screen.
Yes.
Perfect. Perfect. So yeah, good morning, everyone. So my name is Romain Botson. I'm the Actran Product Marketing Manager. And in this last part of this webinar, I would like to give you some insight on how you could rely on JMAG and scFLOW results to build a vibroacoustic model. So you are able to assess the NVH performances of your motor, and therefore maintain the NVH targets that you might have. So in this last part, I will tackle three main points. Basically, how you can model e-motors within Actran, so relying on JMAG and scFLOW information. And most of my presentation will focus on how you can actually analyze the sound emission mechanism of your e-motor. So of course we will compare the different casing that Maxime showed us. We will also understand the impact of the openings he put within this casing. And last but not least, we will see how you can move forward within your CA-led design when it comes to vibroacoustic analysis. So just as a brief summary, when it comes to the sound emitted by e-motors, well, actually the total noise can be divided into three main contributors: electromagnetic noise, mechanical noise, and aerodynamic noise. In today's presentation, we'll focus on the electromagnetic noise that consists in the noise induced by the vibration due to electromagnetic forces. We will see that actually this noise is impacted by the content of the load, so the frequency content of the electromagnetic forces, and of course by the characteristics of the structural geometry of the casing in this case. Mechanical noise are all noise related to the gearing system that we will not cover today, but for which we have a solution. And aerodynamic noise would be the noise due to the flow turbulences, due to the rotation of the motor, for instance, where we could again rely on scFLOW information to compute aerodynamic sources. But let's focus on electromagnetic noise. So how do we couple actually JMAG with Actran? Well, we have seen that JMAG can export different type of information following electromagnetic simulation, and in particular, it can export the electromagnetic loads that are applied on the stator, together with a finite elements model of the stator. So we will start from this input and combine it with the casing design. So we have seen that Maxime was playing around with the design of the casing, and we can also use this information. And those two information will be used to build our e-motor model within Actran. Once we have our model, well, we will compute its vibroacoustic response. We'll do this in the frequency domain to assess the vibrations due to the electromagnetic forces. We'll see that we can access different type of acoustic indicator in order to analyze the performances of our model, and therefore being able to compare the different design and assess what are the impact of the design changes. So these four last steps are performed within Actran. When it comes to the export of loads from JMAG, well, as I said, JMAG will export both the finite element mesh and of the stator, sorry, and as well the electromagnetic forces applied on it. So the EM forces are stored under a UNV file that will contain the forces per node. In our example, well, the engine is rotating at 2,400 RPM, which correspond to 40 Hertz rotation speed. And it is interesting to look at the frequency content of those forces. that are characterized actually by also the number of rotor poles. So in this case, in our case, we have 2 rotor poles, which means that the main frequency content of the forces occur every 160 Hertz. So what we see here on the right hand side of the slide is the frequency content of the electromagnetic forces with, as I mentioned, main peaks occurring at every 160 Hertz. And as we could expect, well, the amplitude and the intensity of those forces is decreasing as function of the frequency. Now, when it comes to the building of the e-motor in Actran, well, I will not spend a lot of time on this because it's really straightforward. So using the CAD geometry for the rest of the motor, we can directly mesh it, and so in order to create our finite element model in Actran. So the CAD is directly imported in Actran, and we use the material property that you can see on the right hand side of this slide to define the different parts of our motor. We applied, in addition to the electromagnetic forces, some boundary condition that consist in fixing the displacement of the housing, so the green part that you can see here, and also connect the shaft to the housing. Now, what is interesting is to focus a little bit on the modeling approach that we are using, because we know that we have a structure that we want to couple with acoustics. So in this case, to build our vibroacoustic model, we used what we call a hybrid approach. So what is it? Well, it consists in modeling the structure by its eigenmodes and corresponding eigenfrequency, so to have a modal representation of the structure, while the surrounding acoustic environment is modeled in physical coordinates. We have what we call a strong coupling in between the structure and the acoustic, meaning that yes, the structure will vibrate and induce noise, but the acoustic could also have an impact on the structure. Well, in this case, because we are radiating in air, actually the effect of the acoustic on the structure will be negligible. What is also worth to mention is that actually the exterior acoustic environment, so the acoustics surrounding the structure, is created automatically by the solver, meaning that the finite element mesh that we use in order to compute the acoustic propagation around the motor is not done by the user, but will be done at the solver side. And because it's done at the solver level, well, actually the mesh will be adapted to the frequency we want to solve. So what you see here on the bottom right-hand side of the slide are the different meshes that will be created during the computation. And as we could expect, well, the size of the mesh is dependent on the frequency. The higher the frequency, smaller the element will be, and on the opposite side, lower the frequency, lower the element size will be. And thanks to that, we can really optimize the total computation cost of our analysis. I will just, remove the pointer if it's possible. We'll see. Sorry for that. So because we use a modal approach for the structure modeling, we can also, before actually launching the final vibroacoustic model, compare the effect of the casing modification that Maxime suggested on the structure itself. To do so, we are using what we call modal assurance criterion, which is a MAC, that consists in comparing the shape of the structural mode. So within Actran, we have a tool that allows you to do so. So once you have the modal basis of the two geometry, you can easily compare the effects resulting from the modification that Maxime suggested. What we see here on the right-hand side is the output of such comparison. And as we could expect, well, actually the perforation that we are adding to the structure is directly impacting the stiffness of the casing, shifting the frequency of the mode to an higher frequency. Now, when it comes to the response itself, what we are looking at in the first time is a comparison of the total acoustic power radiated by the two geometries. So this is what you see on the left-hand side of this slide, where we compare the reference and the optimized configuration. We see actually that at low frequency, the addition of perforation is not strongly impacting the total acoustic power that is radiated, unless only small frequencies are impacted by that, and in particular at higher frequency around 4000 Hertz. I'm sorry for the animation that are not working. And okay. I hope, oops, sorry for that. In addition to looking at the total acoustic power that is radiated by those the two geometries, we can also directly output from Actran what we call the radiation efficiency, that consists in quantifying how it is easy for the geometry to radiate noise. Of course, there is a direct link in between what we see on the left-hand side and on the right-hand side, as the radiation efficiency increases with the frequency, while the total acoustic power that is radiated by the geometry is increasing as well. So here what we see on the bottom of the slide are some maps and animation that allows us to really visualize how the acoustic is propagating around the geometry. Now we can really dive into the understanding of the mechanism behind the sound generation thanks to specific indicator in Actran. In particular, we will look at the modal participation to the structure dynamics. So what does that mean? It means that we are able to understand how the different modes are contributing to the final vibration of the structure. So what we see here on the right-hand side are those modal participation factor as function of the frequency. So on the y-axis, we have listed the different modes. On the x-axis, the frequency range that we are using for the computation, and the color give us an idea on how one mode is contributing to the final response. And we can directly spot that some modes are more contributing than others by looking at just the red and orange color. And though if we look at those modes in particular, so they consist in higher frequency mode with a specific deformation. And actually, when we look at this deformation and compare it with the stator geometry, well, we understand that because there is a match in between the electromagnetic forces pattern and the mode, this is why those modes are more contributing than the others to the total, the final deformation of the casing. So some mode of the housing and rotor are highly excited. But it's not enough to understand what's really happening. What we need to look at is also if one specific mode, even if it's highly excited, is it able to actually efficiently radiate noise. And for that, we are looking at another indicator available in Actran that consists in the radiation efficiency of each of the structural modes. And this allows us to also filter the problematic, let's say, mode. And in particular, we can understand that some torsional modes, well, are not at all able to radiate. Now, if we combine those actually two information, we can really spot modes that are highly excited and that can efficiently radiate noise. So typically, those will be the modes that we might work on in order to reduce the total noise of the engine. We can also filter some structural deformation that will not contribute to the total noise. And so therefore, by looking at all these indicators, we can, if we have an issue within the final NVH response of our system, we understand on what we should focus on and where we need to potentially make design changes. Now, in our case, because we are also, let's say, increasing the openings of the casing in order to let the flow go through it, well, we wanted to also assess the impact of the interior acoustic cavity of the engine. So we know that we have openings in the casing, that when we increase these openings, well, we'll have a larger connection between the interior cavity and the exterior acoustic environment. And in Actran, you can actually easily model this interior cavity, as well as, for instance, the perforation that you have on the casing, by simply adding an acoustic volume representing the interior cavity and coupling it with the model that we previously built. So on this slide, we are looking at the comparison of one configuration, so the optimized configuration with more openings, and we are looking at the differences in terms of acoustic power with or without considering the interior cavity. So what we see on the left-hand side is that we have a small impact on the of the cavity on the total emitted power. Even for some configuration, it's somehow reducing the total emitted power. Again, only at high frequencies. Well, the total emitted power by the system is higher when we consider the interior cavity. And therefore, we can also compare the Hall effect in between the reference and optimized configuration. So this is also one unique capabilities of Actran, because it's a dedicated tool for vibroacoustic analysis. You can consider more complex acoustic phenomena that you would have in other tool. And we can go further because actually we know that our motor is not an isolated system. It will be embedded in a more complex environment, and in particular, we potentially want to consider all the acoustic treatment or thermal treatment that will be around our engine or directly put on top of it. So we talk about complete encapsulation, for instance, to really reduce the sound that is emitted by the engine. We can directly model those effects within Actran, as we can also consider more complex geometries with acoustic treatments such as powertrain, partial cover, or underhood thermal acoustic liner when it comes to the automotive industry. So while working with Actran for electric motors, well, we've seen that we can have an accurate vibroacoustic representation of the motor behavior, accessing specific indicators such as radiation efficiency that will really help us to understand what's happening and what we should potentially modify on the system. Actually, the coupling in between JMAG, scFLOW, and Actran can be really streamlined with automation capabilities of Actran. You will be able to access subjective evaluation of the NVH performances of your system. And as I mentioned in the last slide, well, once you have this model, actually you can use it in a more complex acoustic environment to really assess the integration of your system and understand where you should potentially put acoustic treatment around it. Of course, we will support you, so you will be guided by our team to help you at the beginning to build your first model. So thanks a lot for your attention. And then I think now we can open the Q&A session. So if you have any question about JMAG, scFLOW, or Actran, please let us know.
Okay, thank you, Roman. So okay, so I think we have some question. I have some question from Mahdi Hassan. So the question is, does IP protection of motor enclosed affect natural convection as a result efficiency go down? Let's say IP protection of 5423 of same motor, is there going to be much different?
I think this one is for me. So thank you for this question. So I would say in a generic perspective, the higher your protection will be, the less you have in terms of possibility to open the housing. So of course it will affect the thermal behavior. In the example I show you, so we have a decrease of 15 degrees. This opening were 6 millimeters wide. So I'm not an expert about the different levels of protection and what it implies in terms of constraint in the design. But just to give you a first taste that a slight modification can really improve or worse a design. So yes, definitely it will affect the behavior that you can have inside the motor. And that's where CFD can bring for sure a good value to quantify it.
Okay, thank you. Another question? Do you have another question? Okay, so if there is no question, so we can end this webinar. So thank you for every attendee to join this webinar. So feel free to contact us if you have any question about JMAG, scFLOW, and Actran software. So thank you and bye.
Thank you, everyone.
Thank you, everyone. Have a good day.
Thank you. Bye.